Hello everyone, I am Namita Jain. So today we are starting with the topic of Huffman coding. Okay, और ये जो टॉपिक है ये बहुत ही इम्पोर्टेंट टॉपिक है. हर एक एग्जामिनेशन में इसके क्वेश्चंस नॉर्मली आपको पूछे ही जाते हैं. तो आज हम इस टॉपिक को कंप्लीट करेंगे. So let's discuss the things about the Huffman coding. Let's have a brief idea about Huffman coding, and then we will be doing some of the examples related to Huffman coding. Okay, so let's say there is a file and you want to compress that file, the size of the data. Okay, so sometimes you might have seen such things, it always happens. So let's say that we have a file in which we have only 4 characters. Suppose I have this file, and in this file I have only 4 characters, and every characters we are encoding in the form of zeros and ones. Okay, so that it can be saved onto the disk or it can be transmitted. Now for encoding these 4 characters we need 4 bits. So it can be let the characters be A, B, C, D. Okay, and for encoding these 4 characters we need 4 bits. So it can be 00, 01, 10 and 11. It can be like that. So let's say that this entire file is made up of A, B, C, D. This file has A, B, C, D, A, B, C, D in total written over here. And it has no spaces, no digits, nothing is there inside the file except this. Okay. So let's say that this entire file is having 100 characters. This entire file is having 100 characters. Then how many bits are required to represent the entire file? The question is how many characters or how many bits are required to represent the entire file. So if we have 100 characters, then every character is requiring 2 bits, right? So it is equal to 100 into 2 is equal to 200 bits are being required. Okay, so I need 200 bits to represent this entire file. Now can I save same file using less number of bits? That will be more better, and that will be the more efficient way to do the things. Okay, so if distribution of characters are not even, here the distribution of the characters are even distribution are there, or we can say it is the fixed distribution which is there. Okay, so if the distribution of characters are not even, that is I can say if occurrence of A, B, C, D are not all the same, then we can use the Huffman codes, so that I can reduce total number of bits required to store each character. So let me explain this point like this. Let A is occurring 50 times. Okay, B is occurring 40 times in a file, C is occurring 5 times in a file, and D is also occurring 5 times in a file. So you can count, it is 50 plus 40, 90 plus 5, 95, and it is 100. Okay, so these many characters are there which is having so now just check it out which character is having the highest frequency. So of course A is having the highest frequency because it is 50. Okay, so represent it using the least number of bits. So let it be, I have taken it as 0. Let the pattern be 0 for A. Okay, for B let the pattern be 10. For C let the pattern be 110, and for D let the pattern be 111. So I have taken this pattern, and this is basically the uneven distribution of the bits. You can see this is uneven distribution. Here 1 is there, here only 2 bits, here 3 bits. So this is uneven distribution, I can say, which is there, and basically also I can say that it is having the unequal size. The size is not fixed and it is uneven distribution. So earlier it was fixed distribution, it was fixed size encoding, and this is a variable size encoding. So you can say it variable size encoding. This is the same. Okay, and that was fixed size. So let's say I have the string A, B, C, D and E. Let these be the string. Let A be 0 So here the A comes to be 0, B comes to be 1 0, C is 1 1 0, D is 1 1 1, and A is again 0. So when I decode it, I know that A is 0. I have encoded it first, and then whenever I decode it, I know that A is 0. Similarly, and no other code is starting from 0. You can see that the prefix of A is 0, and there is no other code having the prefix 0. Similarly, B is having 1 0, and no other code is having the prefix as 1 0. Similarly, C is having 1 1 1 1 is common, then 1 1 0. So no other code is having the same as 1 1 0, right? So I can say that if I am using any pattern to represent any character, then that pattern should not be the prefix of any other code. That is very important. So if we do such encoding, then let's see if we have any gain in the bits. So here total 50 A's are there. Here total we have 50 A's. So let me take it like this, 50 into 1, because this is 1 bit. Let me take it as 40 into 2, the length is 2 bits. Let me take this as 5 into 3, because this is 3 bits. And this is 5 into 3. Okay, we can write like this. So it is equal to 50, and this is 80, this is 15, and this is 15. If I calculate this, this is 160 bits. This is 160 bits. So we can say that in uniform encoding, I used to get 200 bits. It was uniform or even or fixed, and I was getting 200 bits. While whenever I am taking the unequal size or the variable size, then I am getting 160 bits, which is far more better than that. So it depends upon the frequency. So here I am getting length of the sequence. So there is a gain of the 40 bits. So you can see the difference of 260. That is the difference of 40 bits is there. Okay. Now let us take one example for the same to understand it more clearly. So let's take an example. Let's say that if I have a file, number of characters are 4. I have a file, and in that particular file I have number of characters is equal to 4, and I am taking the same as frequency of A is equal to 50, frequency of B is equal to 40, C is equal to 5, and D is equal to 5. Okay, now you have to construct a tree as per the given frequencies. So how you can do this? First of all, we have to take out the least 2. We have to take the least 2. So this is C and this is D, and the value is 5. Here the value is 5. I'm adding both the values, and it comes out to be 10. Now the next number is 40. Now 40 will come in the right side, because on the right side we are always taking the value which is the bigger value. If it is the lesser value, we are taking it on the left side. If it is the bigger value, then we are taking it on the right side. So I am writing here as B, and the value of B is 40. Okay, then again I have to calculate it. 40 plus 10 is equal to 50. Now again I can see A is equal to 50. When the values are similar, means when the values are equal, then we can take it either on the left side or on the right side. So I have taken the value on the left side. If you want, you can take it on the right side also, it hardly matters. Okay, so this is equal to 100. Is it okay? Okay, so now on the left side you can put zeros, or on the right side you can put zeros. Okay, so one side we have to put zeros, and on the another side we have to put ones. You can take any of the side you can take. If suppose I am taking on the left side, I am taking zeros, and on the right side I am taking 1. Okay, and now what I have to do? I have to calculate the length. So let me calculate the length here. A is equal to, it is 0. B is equal to, B is 1 1. C is equal to, C is 1 0 0. And D is equal to, it is 1 0 1. Okay, So now here I will be multiplying length with the frequency, and here the length is 1, the length is 2, the length is 3, and the length is 3. So I'll do like this. This is A. So this is length with the frequency. This is frequency and this is the length. Plus 40 into 2 plus 5 into 3 plus 5 into 3, and it comes out to be 160 bits. Okay. So this particular, whenever I am multiplying length with the frequency, this particular is known as the weighted external path length. This is known as the weighted external path length, right, whenever we are multiplying the values. So in this file I am sending 100 characters. I was having 100 characters, 50 plus 40 plus 5 plus 5, and 160 bits are used to send it. So the number of bits per character which are actually used to store this file is 160 divided by 100, that is equal to 1.6 bits per character, right. So here I am using 1.6 bits for one character. So like this you can do this question. Okay, so let's take one more example of the Huffman coding. So here I am assuming that there are some nodes and there is some frequency given here. So let the nodes be A, B, C, D, E and F, and the frequency be 40, 30, 20, 5, 3 and 2. Alright. So we have to put all the nodes in some data structures and then we have to take the minimum. So as we have done in the previous example, similarly we are doing here also. So the last two, these values are the least values. So let's start with the same. 2 is the smaller value than 3. So let me take here. This is F and this is E. No, we can take it like this. This is F because this is the smaller value and this is the bigger value. So this is F and this is E. So F is 2 and E is 3. So then we have to add these values and this comes out to be 5. This is okay. Then the next value is D is 5. So we can take D on the left side also or on the right side also because the value is equal. So I'll be taking it on the left side. If you want you can take it on the right side also, no problem. Okay. So I am taking it here and it is 5 plus 5, that is equal to 10. Alright, now the next value is, these three we have completed. Now the next value is C is 20. So 20 is bigger than 10. So I'll take it on the right side and here I am taking C is 20. Now we have to add these values and it comes out to be 30. Alright, then we have to take the value for B. And B is 30. So again it is an equal value. I can take it on any of the sides. So I am taking the value here. It is 30. So let us calculate the values. The values are 60. 30 plus 30 is 60. Then again A is 40. So 40 is less than 60. So I am taking it here 40. And then again we have to add these two values and it comes out to be 100. Okay, it comes out to be 100. Now again on the left side you can put zeros or on the right side you can put ones or vice versa. So I am taking the values like this 0, 0, 0, 0 and all. And on the right side I am taking 1, 1, 1, 1. Like this I am taking the values. Alright. Now the same thing. A is equal to, it is 0. B is equal to, it is 1, 0. C is equal to, this is C, it is 1, 1, 1. D is equal to, where is D? It is your 1, 1, 0, 0. This is D. then E is equal to, it is 1 1 0 1 1, and then F is equal to 1 1 0 1 0. Alright, so the frequency is 40, so length and multiplied by frequency, so this is 40 multiplied by 1, this is 30 multiplied by 2, this is 20 multiplied by 3, this is 5 multiplied by 4, this is 3 multiplied by 5, and this is 2 multiplied by 5. So whenever I am multiplying all these values and adding it, then I am getting here as 40 plus 60 plus 60 plus 20 plus 15 plus 10, and it is equal to 205. So 205 means these are the average number of bits which are used per character, and the total was 100. If I am combining all these values, again it is 100, so it is 200 divided by 100, that is equal to 2.05. So here I am using 2.05 bits for one character. Okay, and you can see that every character is at the leaf node. You can see any of the character, and every character is at the leaf node itself. Okay, so this always you have to keep in the mind. So I think now the examples are clear and you can do the questions if it comes. Now let's see about the time complexity. Sometimes the question is being asked like, what is the time complexity for this? So the time complexity is definitely it is your order of n log n. So this is the time complexity for this Huffman coding. And if the space complexity is being asked, like what is the space complexity for the same? So the space complexity means you count number of nodes in the tree, and it is nearly order of n. So this is basically the space required to represent the entire tree, and which is your order of n. So this is the time complexity and this is the space complexity. I think the topic is quite clear to all of you. So thanks for watching my video, and if you like my videos, please like, share and subscribe my channel. Thank you.